Hi, I'm Teacher Tyler, and this is Newtonian Physics. Today we're going to talk about uniform circular motion. We're going to talk about Newton's first and second law. We're going to do examples based on conical motion of a pendulum. We're also going to do examples of finding the velocity of a conical pendulum. And we're going to do one example of a banked turn with friction. And that will cover the chapter. According to Newton's first law, the puck, or particle, would move in a straight line if there were no force acting on it. However, this is uniform constant motion in a circular motion, right? So there is a force acting on it, which is called centripetal acceleration, and that is the force pulling inward. If you are in a different frame of reference, you are in the middle, you would actually call it centrifugal force. Before we go into the Ferris wheel example, it's important to note a few key concepts when you're deriving from your solutions. Now let me explain. Key concept. What are your forces? Now, in the Ferris wheel example, we'll be able to describe those forces. But the concept is, when you have a question and you have to derive a solution, you must be able to draw a diagram of your forces. So, what are your forces? In addition to, what is acceleration? Acceleration is the key point in the Newtonian physics and the F equals ma, Newton's second law. There are 4 key questions posed. 4 solutions to derive. Each solution will be different. Do not, I repeat, do not memorize your equations. Each one has to be derived separately. For example, the question can be posed in the form of, what is the tension? What is the angle? What is the height? Or, what is the maximum velocity? Steps I recommend as your teacher to help you remember in deriving your solutions, because you will be alone on your exams. Step 1, draw a diagram. Step 2, draw the forces. And I highly recommend you use different colors.
In the example of the Ferris wheel, I've gone a step further and to illustrate the normal force and the net force, with also the force acting downward, mg, the mass times gravity, because F has to equal something, mass times gravity. So the normal force minus mg will balance out to 0. So 3 forces acting on you when you're at the top of the Ferris wheel, 3 forces acting on you when you're at the bottom of the Ferris wheel. We must label our positive and negative. We have to show which one is positive in order to derive our equation. Now those can be interchangeable. If you want to choose that up is negative, you can do that. Down is positive, you can do that. Just make sure that you write your equation in the fashion that you have chosen. And make sure that the normal force is minus mg equals 0. So therefore, the normal force is equal to mg. At the top of the Ferris wheel, we have mg minus the normal force is equal to ma. So the normal force, when you algebraically rearrange this, you have the acceleration of the Ferris wheel, gravity, mass, and normal force at the top of the Ferris wheel. And at the bottom of the Ferris wheel, you have Fn, the normal force, minus mg equals ma. And when you algebraically rearrange it, you have a positive sign. And you can derive your net forces at the top and at the bottom using the equations I have shown. Now you must be able to do this on the exam. So the top and the bottom using different colors, and we have normal force in 3 locations. We have drawn consistently, we have shown our work, and we have also labeled positive and negative directions.
So we know we're modeling centripetal acceleration. And examples of modeling centripetal acceleration are tension in a string of constant length, and forces which I find particularly intriguing: gravitational force, magnetic force, and also electronic force. So this is important for your career path, because you can take this into astrophysics, you can take this into electronic engineering, you can take this into civil engineering. And these 3 career fields will require the use of the conical pendulum model and uniform circular motion equations, especially an in-depth understanding of Newtonian physics and F and the sum of the forces equaling the mass times the centripetal acceleration, where centripetal acceleration is equal to the mass times the speed squared divided by the radius of the object. Now again, this can be a gravitational force acting on a planet, magnetic force acting on a charged particle, or an electronic force acting on an electron in orbit around a nucleus.